Okay, so now we're ready to start talking about applied optimization problems. So just like with curve sketching, this really isn't anything new. We're just going to take stuff that we've done before and apply it to a different kind of situation here. So, and also just like with related rates, applied optimization has a general process we can follow. And this exact process isn't going to work for every single applied optimization problem. But for the most part, it is going to get you to where you need to be. You know, you might have more complicated problems that have more going on. But in general, follow this kind of procedure here and it'll work out. So let's go through these as we do example one. So example one says find two positive numbers such that their product is 256 and their sum is a minimum. Okay? So step one is draw and label a picture if possible. So here, that's not really possible here because we're talking about sums and products of numbers, so nothing geometric is happening. Also part of step one is assign variables to all the quantities in the problem. Okay, so we're talking about two positive numbers, their products is 256, then we want their sum to be a minimum. So let's say let x and y be the numbers. Okay. Now we are talking about a product, but we know the product is 256, it's a constant, so we don't have to give it a variable. You can if you want, but it's really not going to do anything to help. So let x and y be the numbers, and let s be the sum. Okay, because the sum is what we're trying to minimize, so we should call that something. Okay, let's call it capital S for sum. All right, so that's step one. Couldn't draw a picture. Then we just assign variables to the variable quantities. 256 is a constant, so we don't have to worry about a variable there. Now step two, write an equation for the quantity to be maximized or minimized. Here we're trying to minimize S, okay? And what is S? It's the sum of x and y. So big S equals x plus y. Okay. So big S equals x plus y. That's it for step two. Okay, write an equation for the quantity to be maximized or minimized. That's it. Now step three. Okay, so the problem here is, we want to minimize this, right? But it's in terms of x and y. So we don't really know how to minimize functions with two variables. So what we want to do is reduce this guy down to a function with one variable. And that's what step three is. Reduce the equation to one with a single independent variable. Okay, so x and y are the independent variables, and s is dependent because it depends on x and y. Okay. Now this may require secondary equations that relate the variables to each other. So in general, once we get to step three, what we want to do is ask ourselves, do we have any other pieces of information that we can use to relate the variables to each other? So in this case, do we? And yeah, we do. We know that the product of x and y is 256. So in other words, x times y equals 256. Okay. Now, how's that going to help us? Well, that's going to help us express one of the variables in terms of the other, and then we can take that expression and stick it back into this equation here. So xy equals 256. Let's solve for y in terms of x so that we can put that into this equation here, just have it in terms of x. So y equals 256 over x. Okay? So we're going to take this and we're going to stick it on up into this equation here. Okay? So now this becomes s of x equals, that x is still just x, and then this y becomes 256 over x. Okay, so x and y are variables, but no matter what's happening, this relationship is always going to be true because x times y is 256, so this relationship is also always true. Okay? And you might be thinking about, what if we divide by 0? That's bad, but it's okay because both these numbers are positive. Okay? So anyway, that's it for step three. Reduce the equation to one with a single independent variable. So now s of x equals x plus 256 over x. It's just one equation in terms of x. And we know how to maximize and minimize stuff like that, right? So that's good. Now before we do that though, step four, find the domain of the equation found in step three. So, and really this is just a function of one variable, and we got to find the domain. So, and we have to be careful because we do have additional restrictions besides just the restrictions that we get from looking at the function. So here, the only restriction that we get from the function is that x can't be 0. But we also have this additional restriction here, okay, that x and y are both positive. So x has to be strictly positive, strictly greater than 0. So the domain is all the positive real numbers. Okay. Now you might be thinking, well, shouldn't we cap it on the top at 256? Well, x can really, in theory, x could be larger than 256. Okay, like x could be 512 and y could be a half. Those are both positive numbers. Okay, these don't have to be integers or anything like that, just any two positive numbers. So really the domain is just all positive real numbers here. Okay, so that's it for step 4. And again, I just want to point out, don't just look at the domain of the function, look at what's happening in the problem. You might be constrained some other way. Like here, we're just flat out told two positive numbers. But for more complicated problems, you might be restricted by the geometry of the situation. But we'll see some of that in later examples. So anyway, step 5 now, use calculus techniques to find the desired quantity. So in this case, the desired quantity of the two numbers here. Okay? And again, we don't care what the minimum sum is. We just care that we get these numbers that minimize the sum. Okay, so now calculus techniques. So let's do the second derivative test. So here s of x equals x plus 256 over x. So s prime of x equals, there's a lot of different ways we could approach this. Let's go ahead and do it, let's do it like this. So that's going to be 1, or you know what, before that, sorry about that. So let's rewrite s like this. S of x equals x plus 256x to the negative 1. Okay. Let's rewrite this term like this, 256x to the negative 1. So then when we take a derivative, okay, this first term is still going to be 1, but now what we can do is say plus 256 times negative x to the negative 2. So all we did here was just a power rule, okay, just a power rule. So if you don't like that, you could do like a quotient rule thing here. You could combine this into one fraction and then do a quotient rule on that. That's totally fine. It's really up to you, just personal preference. So anyway, this is going to be 1 minus 256 over x squared. Okay? All right, so, or we could write that as 1 minus 256x to the negative 2. Okay. So I'm writing it like this so that when we do the second derivative, it's going to be easier to use this. So anyway, that's our first derivative. Now we want to set this equal to 0 and solve for x. Okay, in other words, what are we looking for? We're looking for critical points, right? Why are we looking for critical points? Because we're trying to minimize this, okay? S of x, that's the sum of x and y, but it's expressed in terms of just x. Okay, and we want to find the numbers x and y that minimize the sum, all right? So that's why we're taking the derivative of s, so that we can actually minimize it and see where does that minimum happen. All right, so now we find the critical points, so set this equal to 0 and solve for x. So a lot of different ways to approach that. Let's do it like this. 1 equals 256 over x squared. Multiply both sides by x squared. In general, you have to be very careful about that. Make sure you're not multiplying everything by 0. But that's okay here because we know x has to be strictly positive, so it's okay to do that. So now we take a square root of both sides. And remember, always take the negative root also, so x equals 16 or negative 16. Okay. But negative 16, we can just throw that one out because remember, x has to be strictly greater than 0, right? So we can just toss that one out. So x equals 16 is our only critical point that we get from here. Now we can also get critical points, what's the other way? By figuring out when is the derivative undefined. Well, this derivative is undefined when x is 0, right? Because then we're dividing by 0. But 0 is not in the domain. Okay, so to be a critical point, you have to be in the domain of the original function. But 0 is not, so we just don't even have to worry about it. So our only critical point is x equals 16. Okay? And again, I just want to point out real quick that what we're doing right now is just minimizing a function, so we can totally forget about the application once we get to step 5, for a little bit anyway. Then after we finish step 5, we have to go back to the application. But here, all we're just doing is taking a derivative, setting it equal to 0, figuring out where it's undefined, just looking for critical points. That's all we're doing. So x equals 16, that's 1. So what we could do is set up a sign chart like we did with curve sketching, but we don't really care where anything's increasing or decreasing. We only care, is it a max or is it a min? So what we could do is the second derivative test. So in this case, the derivative isn't too bad, so let's go ahead and do that. So if s prime of x equals 1 minus 256x to the negative 2, then s double prime of x equals 0 minus 256 times negative 2x to the negative 3. Okay. So again, that's just power rule right there. So this 1, take a derivative, becomes a 0. Then here we just did the power rule. So minus 256 is a constant multiple, and then x to the negative 2 becomes negative 2x to the negative 3. So then s double prime of x equals positive 512 over x cubed. Okay, so that's s double prime of x. So now if we're doing the second derivative test, we got to figure out, okay, what's s double prime of 16? So let's come over here as we're, well, yeah, let's come over here as we're kind of running out of room. So S double primed of 16. Okay, so take our critical point, stick it into the second derivative. S double prime to 16 equals 512 over 16 cubed. Okay. Now, what is that? I don't know, some big number, 16 cubed. We don't really care what it is though, right? We just know that it's positive, okay? 512 is positive, 16 cubed is positive. Positive number divided by positive number is positive. Okay, so S double prime to 16 is greater than 0. So what does the second derivative tell us? The second derivative tells us that, therefore, S of x has a local minimum, as a local min, at x equals 16. Okay? And so that's kind of it for step 5. Now we just have to wrap it up and answer the actual question. So S of x has a local min at x equals 16. So the question, the original problem was find two positive numbers such that their product is 256 and their sum is a minimum. So we found one of them, right? One of them is x equals 16. Now we have to find y. So how do we find y? Well, we go back to this equation here. Okay. So really, either one of these, we might as well just use this one because this one gives us y in terms of x. So if x equals 16, or since x equals 16, then y equals 256 over x. And in this case, x is 16, so y equals 256 over 16, which is 16. So the numbers are x equals 16 and y equals 16. Okay, so that's it for example 1. So not really too bad. There's nothing geometric or crazy happening like that. Just the function's kind of goofy. You know, it gets a little messy, just a little tiny bit with the derivatives, but it's not too bad. So that's example 1 with applied optimization. And again, we don't care what the sum actually is, right? And this, you know, it is 32. X plus y is 16 plus 16, which is 32. But we were only asked to find the positive numbers. We don't care what the sum is. So always make sure to be careful of what you're being asked. So here, that's it for example 1.